on finite categories with coefficients. And the prototypical example is the work of Simpson and Smith. Okay. So the work of Simpson and Smith is for the case of SL2. So there's an idea which is that spectral curve sigma inside the cotangent bundle of a Riemann surface. So here X is a compact Riemann surface. Well, compact or non-compact, X is a Riemann surface, let's say. So if we have a spectral curve sitting inside the cotangent bundle of a Riemann surface, then we can think of a certain number of Fukaya type categories. So we can look at sort of a Fukaya category of the cotangent bundle itself.
I'm sorry, do you mean that there is a Higgs field somewhere? What do you mean by that?
Well, suppose we just have a spectral curve to start with. Then this will be the spectral curve of a Higgs field.
So why it is just some curve?
Yeah, a curve, but that means that it means that its projection to X is proper. So the map from sigma to X, this is proper and it's R to 1 if that corresponds to the group SLR. And for the group SR, it means also that the sum of the elements in the fiber equal 0. The trace of the Higgs field equal 0. So we can try to find some kind of Fukaya category of the cotangent bundle relative to the spectral curve. And then another thing we can do is we can try to define some kind of three-dimensional manifold mapping to the cotangent bundle, which has so fibers are P1, and that's kind of with singular locus over the spectral curve. Okay, so maybe let me draw a couple of pictures. So in the first case, 1, 2. In the first case, the picture looks like this. So if we have the spectral curve like that, remember this is a complex picture, but we're kind of drawing the real picture. If we have a spectral curve like that, then we might have Lagrangians which connect two different fibers of the spectral curve. Okay. And this line over a Lagrangian graph in the base. Okay. So over a Lagrangian graph in the base, then it might have some endpoints. You could sort of, over each point of the graph of the line in the base, you could connect the two of the different fibers of the spectral curve. That's going to make a Lagrangian upstairs. In the case number 2, it's closely related to this. So we have the spectral curve like that. Then we have inside C, we have Z is kind of a conic bundle over. So this is inside Z. So inside Z, instead of connecting the fibers here, I mean, in some sense, Z is number 2 is obtained from number 1 by, again, going to another fibration. Okay? So this means that these connections between 2 points here, we replace them by spheres that join together the vanishing points. So sometimes, so the lines here get replaced by thimbles up here. That's just kind of motivation here. So then, so I guess there's some way of interpreting. Let's direct any questions to Luke. Okay. Some way of interpreting what Simpson and Smith are doing in terms of one of these two pictures. Maybe the difference between these two pictures is that in picture number 1, the fiber is going to be A, R minus 1. And picture number 2, I guess the fiber is going to be A R minus 1 CY2.
The fibers of what?
So this is we have some this geometric picture of a vibration over the base X is reflected by some kind of sheaf of categories in quotes. And we're trying to look at some kind of Foucault category of sections. Well, I'm going to say more about this tomorrow, in fact. This is just for motivations. So let me explain the motivation, which is that it turns out that in Birchall and Smith work, so Birchall and Smith is the case of SL2C. So the spectral curve is a two-sheeted cover corresponding to a quadratic differential. And so for Birchall and Smith. R equals 2. The spectral curve sigma corresponds to Q, a quadratic differential. And it turns out, for reasons which I think still remain somewhat mysterious, but it turns out that the stability condition, so to define the stability condition, it turns out that we use the foliation. So one uses the foliation, the real foliation, defined by real of Q equals 0.
So is the stability condition on that category or on that?
Yeah, the stability condition on this Foucault category of which I'll be discussing tomorrow, of sections of the sheaf category A. So what this means is the elements here are basically going to be graphs inside X, together with over the graph a section of the sheaf category A.
So it's local sections over this graph?
It's local sections over the graph. I'll try to discuss that more tomorrow. What I just want to explain now is that in the Birchall and Smith world, the construction used in some essential way the foliation given by the quadratic differential, and in particular some kind of mutations of the stability, some kind of wall crossing behavior corresponds to points, to places where this foliation has what's called a saddle connection. So now let me draw the foliation. So the foliation is typically going to look something like this. So this is, Thurston theory and so on, about what does the foliation look like when you have a quadratic differential. So a singular point is something where Q looks like Z to the 1/2 dz, which is d of Z to the 3/2. So the level, if you think about it a little bit, level sets of real part of Q. Those are the level sets where the real part of Z to the 3/2 is constant. And those look something like that. There's a three-prong singularity. The reason there's 3 prongs here is because when you go once around the point, Z to the 1/2, Z to the 3/2 becomes minus Z to the 3/2. So there's no sort of uniform direction. Right? If you try to pick a transverse direction, then when you go once around, it gets to minus the transverse direction. But what I've drawn here is a typical what the foliation might look like. It's close to a saddle connection. But so if we look at what happens here, we have this this leaf here, which comes close to this point, but it goes off like that, and this leaf here, which goes here and goes down like that. And kind of the key property of this foliation is that any 2 points can be joined by a path which is transverse to the foliation. So let's join 2 points from here to here.
So is there some genericity assumption on the quadratic differential, or is it always?
If the quadratic differential is generic, and so in particular you can multiply by a rotation. Okay, if you multiply by rotation, that's going to change the real part. If you multiply by general rotation, then there will be no saddle connection. And if there are no saddle connections, then I'm going to draw a saddle connection in a minute. If there's no saddle connections, then we can join a point here to a point there in a way that's transverse to the foliation. So to do that, we go like that. Then we sort of very slowly go transverse to the foliation down to here, and then go like that. So in the middle here, you can almost go from here to here in a way which is not very transverse, but slightly transverse to the foliation. Okay. Now, as you turn, so even if you just take the same quadratic differential but multiply by a rotation, as you tilt that rotation, at some point the picture is going to look like this. And now there's no way of going from here to here in a way that's transverse to the foliation. Right? If you try to go up here, then you have to go up the hill a little ways and then turn around and come back. So at some point in here, the curve is always going to be tangent to the foliation. So when there's a saddle connection, there's no way of going from one point to the other in a way that's transverse to the foliation. And a saddle connection just means a leaf of the foliation that joins 2 singular points. So now Ludmill's question was, can we do the same thing in higher rank? So for spectral curves for SLR instead of SL2, so spectral curves that are multi-sheeted covers, can we do the same thing as Boson-Smith and define a stability condition on some kind of dry category? We're still working on that question. In particular, we're still working on how to even define the category in which we're going to describe the stability condition. But anyway, so now what was the idea that led to this whole detour about into WKB theory? Well, the idea is that, that these saddle connections actually can be viewed in terms of the map to the tree. Okay, so the foliation corresponds to a map to a tree. Okay. So let me just draw the maps to the trees for those 2 pictures, okay? So the tree is going to be the leaf space. So let's just draw the leaf space of the upper guy and the lower guy. So if you draw the leaf space of the upper guy, then we have pretty much each of those sectors is going to correspond to a some segment in the tree. So, so this point here is the leaf that goes through this singular point. Okay. Then this point down here is going to be the leaf that goes through the other singular point. So, going out from the upper singular point, we have a segment corresponding to all those leaves that are above in the picture. Then we have another segment that corresponds to all those leaves that go off in that direction. And here we have all the leaves that go down. And there we have all the leaves that go off in that direction. And here's the leaves that go in between the two. Okay? Now you can see that when this deforms to the picture with a saddle connection, the tree becomes just a single point, which is the leaf, the common leaf going through all the singular points. And now this has 4 segments. Okay? So, I mean, in our point of view, it's kind of clear, shall we say, that whatever is going on here with the foliation and so on is reflected in some way in the picture of this tree. So here we have a tree that does that, then it's going to go like that. if you think about it, if you draw the next picture in line here where you continue to rotate, then if you continue to rotate, this is going to mutate the tree, basically. Mutate the tree.
So you want the tree to be trivalent?
Well, the tree is not going to be trivalent at this point, because at this point we have 4
Yeah.
natural pigments. And at a general point, it's going to be trivalent.
And this is a good situation.
The general point is, so we said a good situation. Actually, the more interesting situation is the non-general one, but yeah, the generic situation, it's a trivalent tree. And it looks like that. So the point is that these two guys come together, and then if you think about the picture in the other direction, it's going to go like that. So from that, so judging from this picture, and this was kind of fun in what I was discussing this with us. But then from this picture, we decided to look at to kind of do another project, which is to say, so the idea is that a tree for SL2 is going to correspond to some kind of building for SL. So that's the motivation for our investigation of harmonic maps of buildings. Okay?
Building from SLR, where R.
Well, if we have a group, we started with the group SL2 and we came up with a tree. Okay. The idea here is just that you might say a totally mnemonic idea, which is that if you start with the group SL2 and you get a tree, then you expect that if you start with the group SLR, for R bigger than or equal to 3, that you're going to get some kind of a building. Okay. So that's the motivation. Probably kind of hard, but okay. So now let's just go to building behavior. So, well, there's other parts of the motivation, which is that we also know, kind of by general, well, at least Lugo said this in any case. So we know that the stability condition, so the stable objects of the stability condition are supposed to be supported on Guyot-Mornitsky spectral networks.
All this stability condition on board.
Well, the one that we're looking for. Which is the subject of tomorrow's talk, whatever I can say, which is not right, but this is just motivation. But we're supposed to have this Fukana category XA. Okay.
And what is the support for an object of this category?
So remember, the object of this category is a graph with over the graph a section of the sheet category. What I'm saying is that the stable objects for the stability condition are supposed to be things where the graph is a spectral network. Whatever that is. But, so I think we'll see what a spectral network is today. But, so what's the other kind of component of this motivation, which is that Guyot-Mornitsky, we're talking about WB.
What is WB?
Well, that's what I'm about to say. Wenzel, Kramer, Gouin, which I mean, I'm sure you guys call that something else. I think this is good as some Russians might be going for something like that. But, it is somewhat similar to what's called, what's it called? KAM, Carl Moser. CAM, yeah. It's not, I mean, depending on how these things get run around in the literature, they can or might not be the same thing. I'll show you that in a minute. But okay, so the other part of this idea, just part of mnemonic idea, was that if we want to look for a building, then and we want to have spectral networks play a role in some way, then the idea is to look for a building WKB. For the spectral. That's one way, the WKB problem is one way that the spectral curve in the Brigstone-Smith situation for SL2, that's one way that the spectral curve leads to the tree. The next way. So now let me explain WKB. Okay, so suppose we have a system of differential equations of the form. So now here is just z is going to be a complex variable. Suppose we have a complex variable. We look for a vector. So suppose we have a vector which is a function of c, and we try to solve the equation b primes, dv dz equals a index t of z times b, where so t is an extra parameter. So t is an extra parameter which is going to go to infinity in the positive real direction. And we're going to say, suppose this matrix looks like t times the diagonal matrix. Let me also say that this is all supposed to be in SL. That means that the tracing is
Between the derivation on the left hand side, is it over t or z?
z.
The same as the direct?
There's two parameters. There's z and t.
But solutions also depend on t.
Solution depends on t, yeah.
On both t
Yeah, totally.
and
I mean, the letter z is the same on the left and the right side.
This is z, z, z.
Looks very different.
Is that the correct? So it's something like this. So of course you can modify this a little bit. This can have sort of lower order terms in power to t inverse and stuff like that. But this is kind of the basic setup where we have another WKB kind of question. So we have so just an ordinary differential equation depending on a large parameter, and you can always, in local terms, you can always away from singularity turn it into a case like that, because whatever the large part of this matrix is, you could diagonalize the large part of the matrix. Diagonalizing the large part is going to give you a gauge transformation, but doesn't depend on t. So the gauge transformation can be absorbed into the other part of the matrix. So you can always assume that the big part of the matrix is diagonal.
So what are the conditions on B?
Well, everybody's holomorphic function of t.
And B doesn't depend on T.
B does not depend on t. Or if you like, it might depend on t, but it's bounded at the moment on t. Now, what do the solutions look like? Okay. So the classical case, I think I will not do that here. Just a picture. So classical case. So suppose we have points P and Q and a path gamma from P to Q. And suppose that gamma upper star of AI of Z dz is equal to, say, alpha I of S yes. So gamma is a gamma is a function from the interval into the complex plane, the z plane. Well, let's call that coordinate S. So suppose that gamma upper star of the differential forms are given by some just functions, real functions, complex value functions of S, such that the real part of alpha 1 is strictly bigger than the real part of alpha 2.
Is it possible to distinguish between S and Z
Yeah.
in the argument?
So yes,
And on the left hand side, is it Z?
this is Z.
Okay.
Okay, don't mind. Okay, so suppose the classical case is suppose that these guys are well ordered in the sense that the real part is strictly decreasing. Okay? In that case, we know how to solve the equation. So in that case, the transport function from P to Q. So this is a function that depends on T, okay? This is going to look like approximately like e to the t times integral from P to Q of A1 of Z. Well, what does this approximately mean? Well, it's not all that. It's an approximation, but the order of growth of this transport matrix. So this is the transport matrix for the solution of the differential equation. It says the matrix from Z equals P to Z equals Q. That solves the equation. And more precisely, we can define the exponent. So let's remember that t is going to infinity in the positive real direction. Okay? Operator on.
So, I'm sorry, I mean, the condition depends on the choice of the parts, and the result does not.
Yes, that's true. So that's an important point, which is that we would. So that's why this is. That's why what I said up here in the SL2 case is important. Okay. So in the SL2 case, we can always choose a path that satisfies that property, depending on what if they're aside from the non-generic. For generic values of the angle, you can always choose a path that satisfies that property. That property basically means that the path is transverse to the foliation. Of course, when you move things, then you might change the path. But since it's a holomorphic differential equation, the solution of the differential equation does not change the path. And the basic thing that's happening for r bigger than or equal to 3 it's not always possible to it's not always possible to choose a good path. What else? I don't know. So now what do we do? So let me just well, so let's just say, so this is where buildings come in. So let me just, maybe for people who are more arithmetically oriented or something like that, just kind of briefly say that what you can think of doing here is we can think of this whole setup as being some kind of representation of some fundamental group or something like that. I mean, it's a fundamental group point when I say it. With values in some kind of ring of functions of this variable t. Okay? And we have a valuation on the functions of t, which depends on the growth rate. Okay? So if we take a function of t and we take 1 over t times the log of that function, and take the limit, right, or lim sup maybe, that's going to give you some valuation on the function. So you can, roughly speaking, think of having some kind of field with the valuation. And when you have a representation of the fundamental group or the fundamental groupoid into a SLR of a field with evaluation, it's natural to think of having an action of the groupoid on a building. So that's kind of, roughly speaking, what's going on here. In this precise case, we can just apply the theory of topology find our lead, which is really, so you guys, your question of what is WKB? So you might say the WKB problem is really most totally basic question. It's just trying to figure out what is the exponent, right? Okay, I don't know, does that correspond to KM theory or not in some way? Of course, more precisely, you might want to get some kind of asymptotic expansion for the function and so on. But just the completely most basic question is how fast does this function grow? So we take the point of view that we know the answer in the case of a short path. So if the points P and Q are close together, then you can always choose a nice path from P. So in the general, if the points P and Q are far away, then we're going to apply a theory by Anpao and Kleiner Lieb, which is really based on taking a Gromov limit. Of symmetric Hermitian symmetric space. And we get, what do we get? We get there's a building. So you have to choose an ultrafilter. So an ultrafilter omega, basically on the values of t that are approaching infinity, because you can see the problem here. This limit might not exist. But if you choose an ultrafilter, then it makes that limit automatically exist. These functions are going to be bounded. So just kind of by general estimates for the theory of ODEs, it's going to tell you that this is always going to be bounded. So you can take its limit some way. But you need to specify an ultrafilter if you want to really precisely get the limit and associated types of quantity.
So depend on what? On our class?
On, let's say, the set of t's approaching infinity. For example, if you choose a sequence of t's going to infinity, choose an ultrafilter on n. And then from the ultrafilter, now we can use the ultrafilter to take the Gromov limit. And so what do we get? We get an R building. B. And a map, H. Let's call this B omega. H omega mapping from X into B. Such that this exponent, so let me just call it nu q omega. So nu q omega means that we use the ultrafilter when we calculate the limit. And that this is going to be the distance, some kind of distance. A little caveat is needed here also. This is not really the Euclidean distance in the building, it's what you might call the Finsler distance.
So what are the symmetric spaces?
The symmetric spaces are the symmetric spaces GLRC modulo UR.
I see.
The ones that appear in harmonic in non-dual Hawkes theory. So,
Can you, in 3 words, explain why R equals 2 produces 3s?
well, because as I said, this is basically the Serre. I mean, this is basically the Brouat-Hith building for the group SLR over some kind of a ring with evaluation. The ring with evaluation is, I mean, it's a little bit delicate to say what it is. It's just functions on the real numbers, and the evaluation is this thing here. It's not really a field because your function might have zeros and so on, so you might not be able to invert it. But roughly speaking, it's just it's a building for SLR, and you know the building for SL2 is a tree like Serre. So that's basically roughly speaking what's going on. So then now what's the kind of the theorem? Is that in this WKB situation, the differential, this map is given by the real part of so the building is locally R to the R minus 1. Okay. So an apartment is R to the R minus 1. A typical apartment inside the building is a Euclidean space. So it makes sense to take the differential of the map. This is this. We can think of this as the set of R tuples of elements that whose sum equals 0. So it makes sense to say that the differential of the map. The map is a harmonic map in the Gromov shown sense, in that it sends little neighborhoods in X into single apartments, and the differential is just the real part of the Gaussian cycle. And this fact is really just due to the classical WKB. So I should stop.
So what do you do with these A1 and R? Do you multiply or take maximum or minimum real part?
Comma.
No. So yeah.
Or tuple of
R.
I mean, it means locally the map looks like
And this matrix A, is it going to be the Higgs field in the end?
yeah. It means that locally the map is given by. Right, we need real functions. This is a real Euclidean space. So we take the real parts of functions that are the integrals of the AI. And it's just the formula, right? This is the function G1. If we set G1 of P equals 0, then this integral here, this is G1 of Q. Okay. So if you think about it a little bit, I mean, the Gromov limit, I didn't say exactly what's happening, but the Gromov limit is we're rescaling the metric in a way which corresponds to this operation here. So we take the integrals of the one forms at AI and Z, and we just take the real parts. We think that's locally that's what the map is.
So, I'm sorry, so when you define this H formula, the argument, the point of X, is it P or Q or something else?
Well, the point of X, let's imagine that the point P is fixed, so the point of X is Q, let's say. We're saying that the distance from P to Q is equal to the distance in the building from the base point to the point Q.
So the argument is just one then.
Yeah. So, I mean, I don't have too much time to do this, but if you think about the local picture here, that's just going to tell you exactly this. The local picture tells you that a neighborhood of the point P is all going to go into a single apartment. Just the classical. And the proof of this theorem is just kind of apply the classical result. The only thing we needed to do was to really interpret Perot's result, which was for groups, that we just needed to do a fundamental group Boyd version of that result. So you could have the point P and Q varying, basically. So now, so now comes what you might say the thing which we're interested in doing, which is, it's not very sad, which is we would like to generalize this picture that we have on this board here for SL2. Right, so on this board here for SL2, we have a further information. Okay, so if we think about what this says for SL2, this tells us that the exponent, the distance from here to here, is going to be governed by some map to a tree. In that case, it's a tree. And the differential of the map to the tree is given by the differential form. Okay. So the differential of the map to the tree is given by the foliation. But in the SL2 case, we have something new, which is we have something extra, which is interesting. In fact, that's the thing we're interested in for the stability condition, which is that the foliation determines the tree. Basically, right here we've got a building where we apply this whole WKB theory. We apply this whole Perot Gromov limit theory with an ultrafilter and everything. We got a building. But here we can just see the picture of the tree. Okay, so the question that we were looking at is how can we do the same thing in the higher rank case? Let me just kind of finish by what we have as kind of, this is a project which we kind of have the strategy pretty much written up. This is on our paper. We don't really have the full proof of this. For SL3, and also I should say we don't really know what to do for SL4, SL5, and so on. For SL3, the map from X to the building is going to be subjective, at least on some big open piece. So in the case of SL2, the building has real dimension 1, and our Riemann surface has real dimension 2. So the building is some kind of quotient of the Riemann surface. In the SL3 case, the real dimension is 2 here and real dimension 2 here also. Okay. So we expect that the Riemann surface covers at least some open pieces of the building. In the case SL4, SL5, and so on, the building has a bigger dimension than the Riemann surface, and there we don't have any easy way of touching any points, all the points of the building. So in the SL3 case, at least we can sort of touch the points of the building from the points of X. And so what we would like to do is we'd like to construct, now there's going to be big parts of the building that we can't touch because the building is this kind of big infinite thing. But we have what we can say is that we can construct what we call a pre-building. B A dot. That depends only on these forms. I mean, well, it's not right to be easy here, but these are really differential forms. Okay. Such that our map H from X, H omega from X into the omega is going to factor. Factor in an almost unique way. This is actually sort of versatile. And this is in the case under genericity hypothesis.
And there is no ultrafilter anymore?
Sorry?
There is no ultrafilter anymore?
There's no ultrafilter anymore. Which is a good comment. Let me finish with that comment. The fact that there's no ultrafilter, this implies that the limit is independent of the ultrafilter. So it exists. So what this tells us is that, if we can prove something here, modulo the fact that our program is not completely written down in all detail, but what this shows is that under the genericity hypothesis, this limit actually exists. Whereas to define the building here, we didn't assume it existed, we just used the ultrafilter. But if we have a limit that depends on ultrafilter and we show that it's independent of the ultrafilter, then that proves that the limit exists.
Sorry, the genericity hypothesis on what? The connection mechanism.
Sorry?
The genericity is on what? On connection?
The genericity condition is on the AIs, and in particular on the rotation. I didn't stress that, but you can we're taking t to infinity in a positive real direction. If we multiply these matrices by a rotation, a complex number rotation, it's the same as taking t to infinity in some other direction. So next to the genericity hypothesis is on the direction that t goes to infinity. If t goes to infinity in the generic direction, then no, because in fact you don't expect it to exist in the case where it's not generic.
That was a question. So for the previous statement about refusing to open E to B, what are the assumption of the differential equation?
Well, there's some assumption on the domain because those differentials is sufficient mean. They're not all multiples of the same differential or something. We have three, for SL3 we have three differentials whose sum equals 0. We don't want them to be, we want that to span a two-dimensional space at each point, not one-dimensional. Just so that locally the map is, that's subjective.
And slightly lost, could you repeat, will your statement imply that the limit is independent, or do you need the limit to be independent?
No, our statement will imply that the limit is not.
Okay, so you cannot prove it directly from this theory.
No. So let me stop.
Okay. Let's thank Carlos. Let's postpone the questions for tomorrow.
What did you explain what is the spectral